In this section, we're going to be talking about covalent bonding. And again, much of what we are discussing in this section is a review from our previous chemistry course, but we will be going a little bit more in depth and even more in depth later. So we've just finished talking about how in ionic bonds, electrons are transferred from the metal to the nonmetal. In covalent bonding, the electrons are shared between two nonmetals. The reason the electrons are being shared instead of transferred is because the ionization energies of the two elements and the electron affinities of the two elements are very close to each other. So because there's not a very big difference in the electron affinities, one is not able to completely pull the electron away from the other. Because molecules, covalent bonding, are neutral, the attraction between these molecules is going to be much weaker than between the electrically charged ions. So this is going to cause covalent compounds to have lower melting points and boiling points than ionic compounds do. Many of them are also going to be either liquid or gas at room temperature, and those that are solids are going to tend to be softer than the ionic compounds. Most covalent compounds will be insoluble in water, although there are several exceptions to that. And unlike ionic compounds, covalent compounds are poor conductors in any state. They will not conduct electricity. If you remember, ionic compounds won't conduct electricity when they're solid, but if you melt them or dissolve them in water, then the ions are free to flow, and it will be able to conduct electricity. Covalent compounds will not conduct electricity even if they're melted or dissolved. When we're looking at the length of a bond in a covalent compound, we need to remember that compounds form to become more stable. So the nuclei of each atom attracts those bonding electrons, and the nuclei also repel each other. So here we have the point of lowest energy at the bottom, and that's where the two nuclei are repelling each other the same amount that they're attracting to the electrons that are part of the bond. If they were to get even closer together, then the nuclei would be repelling each other more than they're attracting the electrons, and that would require a lot of energy to stay that way. If they move farther apart, well, then the nuclei still have a greater attraction for the electrons than they have repulsion for each other. Covalent bonds can either be what your textbook calls pure, which we've called nonpolar in the past, or they can be polar. So a pure covalent compound would be one in which the electrons are shared equally, such as between diatomic elements. So if we have O2, each of those oxygens would have the same attraction for those valence electrons, so they would be shared equally. Polar compounds, or polar bonds, would form between different elements, and the electrons would be shared unequally because of the difference in the electronegativity values. If you look up the electronegativity values for hydrogen and for chlorine, you'll see that chlorine has a higher electronegativity than hydrogen does. And remember, electronegativity is the ability for the atom to attract electrons that are part of a bond. So chlorine has a stronger attraction for the electrons, which means it's going to end up with a little bit of a negative charge, and the hydrogen is going to end up with a little bit of a positive charge. That little squiggle thing at the top is a lowercase Greek letter delta, and it just stands for partial, meaning it's not an ion, so I don't have a complete positive 1 charge and a complete negative 1 charge, but I do have a little bit of a charge, so that Greek letter is used to show that. So electronegativity, the ability for the atom to attract the electrons that are involved in the bond, determines how the electrons are going to be distributed. And the greater the electronegativity difference, END, the more polar the bond will be and the larger the partial charge. So if you have a very big difference in electronegativity, you'll have a very polar bond and a very large partial positive and negative charge on those atoms. If the electronegativity difference is small, it'll still be polar, but it won't be as polar as the other, and the partial charges will be smaller. So when we're comparing the polarity of bonds, it's important to remember the periodic trends. And as we go down a group, the atoms are getting bigger, which means those valence electrons that are the ones involved in bonding are farther out, so the attraction will not be as big. So as you go down a group, the electronegativity is going to decrease. And as you go across a period, the atoms are getting smaller, so the attraction for those valence electrons is higher. So as you go across a period from left to right, the electronegativity is going to increase. It's important that we keep straight the difference between electronegativity and electron affinity. Electronegativity is calculated. It's based on an arbitrary scale. There are no units for it. And it's the ability for the atom to attract the electrons that are involved in a bond. Electron affinity is a measurable quantity. It's a measurable value of energy that deals with how much energy is released or absorbed when that atom gains an electron. So when we're looking at covalent bonds, it's always the electronegativity values that we're going to be looking at. The difference in electronegativity will tell us what type of bond is formed. So this is a general guide for bond type. There are exceptions to it. And the type of compound that something forms actually has more to do with its properties than it does the electronegativity difference. But the electronegativity difference greatly influences how it behaves, which is why we can use this as a general guide. If there is a very small difference in electronegativity, meaning less than 0.4, it's considered a nonpolar or pure covalent bond. So even though there might be a little bit of unequal distribution, it's so small it's insignificant. If the difference in electronegativity is between 0.4 and 1.8, then it's a significant difference in electronegativity and it will be a polar covalent compound. If the difference is greater than 1.8, then the difference in electronegativity is big enough that the one with the higher electronegativity would have been able to completely rip that electron off of the other one. So again, there are exceptions to these guides as far as electronegativity difference. And the best way to determine what type of compound you have is actually to look at the position of the elements on the periodic table. So if you have a metal with a nonmetal, it will be ionic. If you have multiple nonmetals together, it will be a covalent compound. If there is a polyatomic ion, it will contain both ionic and covalent bonding. And this is because within the polyatomic ion, you have multiple nonmetals. Each of those nonmetals will be held together with covalent bonding. But it is a group of ions or group of atoms with a charge that's held together to another ion through an ionic bond. Bond polarities play an important role in determining the structure of proteins. Using the electronegativity values in figure 7.6, arrange the following covalent bonds, all commonly found in amino acids, in order of increasing polarity. Then designate the positive and negative atoms using the symbols delta plus and delta minus. So pause this for a minute, find the electronegativities on figure 7.6 in your textbook, and we're looking for polarity. So you want to find the difference in electronegativity, and then use that to put these in order and designate the partial positive and partial negative charges. All right, so there are two here that have equal differences in electronegativity. That would be carbon with hydrogen and sulfur with hydrogen. Both of those have an electronegativity difference of 0.4. So those are the two least polar. The carbon has the partial negative charge. And the hydrogen has the partial positive charge. The sulfur, again, has the partial negative charge, and the hydrogen has the partial positive charge. And again, those were both an electronegativity difference of 0.4. So that's carbon and hydrogen and sulfur and hydrogen. The next biggest is carbon with nitrogen. And in this case, the nitrogen has the higher electronegativity, so this one would be partial negative, and the carbon would be the partial positive. And that was an electronegativity difference of 0.5. The next biggest was nitrogen with hydrogen, which has an electronegativity difference of 0.9. And the nitrogen has the higher electronegativity, so it's partial negative, and the hydrogen is partial positive. Then we have carbon with oxygen, which has an electronegativity difference of 1, and the carbon is your partial positive, and the oxygen is the partial negative. And last we have oxygen with hydrogen, which has an electronegativity difference of 1.4. And your oxygen has the higher electronegativity, so it's partial negative, and hydrogen is then partial positive. So remember, for a polar bond, the electronegativity difference is what determines how polar that bond will be. And the element with the higher electronegativity will be a little bit negative, and the one with the lower electronegativity will be a little bit positive.